I think that I will get started with the introductions. As I said before, welcome everyone to our Center for Bioethics and Social Sciences in Medicine lectureship series. And I have the great honor today of introducing our speakers. So our first speaker, who is Dr. Jessica Ancker, is a professor of biomedical informatics and vice chair for educational affairs in DBMI. Her research centers on the optimal use of information and information technology to improve decision-making. She has a strong interest in health disparities and health equity. In particular, her Making Numbers Meaningful project, which is funded by an R01 from the National Library of Medicine, is an ongoing effort to synthesize best evidence about how to present health-related data to patients. Her Cooperative Effectiveness of Telemedicine and Primary Care project, which is funded by PCORI, is examining the impact of the abrupt transition to telehealth experienced by much of the United States at the beginning of the COVID-19 epidemic in 2020. She earned her master's degree in biostatistics from Columbia and her PhD in biomedical informatics from Columbia's Vaglos College of Physicians and Surgeons. She is also the associate editor at JAMIA and Medical Decision Making and a fellow of the American College of Medical Informatics. So welcome so much, Dr. Ancker. As we know, Dr. Zikmund-Fisher is a professor in the Department of Health Behavior and Health Education at the University of Michigan School of Public Health, as well as a research professor in the Division of General Internal Medicine at the medical school. He is part of the Center for Bioethics and its precursors at U of M since 2002 and acts as the CBSSM Associate Director with me. Dr. Zikmund-Fisher uses his interdisciplinary background in decision psychology and behavioral economics to study factors that affect individual decision-making about a variety of health and medical issues. His research in health communications focuses on making risk statistics and other types of quantitative health information meaningful and useful for decision-making by patients and the public. Dr. Zikmund-Fisher leads the postdoctoral research fellowship program and the Internet Survey Lab at CBSSM, and is a core faculty member of both the U of M Institute for Health Policy and Innovation and the U of M Health Informatics program. He has been named as the editor-in-chief of the journals Medical Decision Making and MDM Policy and Practice for a 5-year term, which ends in 2025, and he has been serving as an associate editor for both journals since 2011. So welcome so much, Dr. Ancker and Dr. Zikmund-Fisher, and the floor is yours, Dr. Ancker.
Great. Thanks so much for having me. I'm really excited to present this work that Brian and I have been working on for about 4 years now and are looking forward to continuing to work on. This is the Making Numbers Meaningful project. Our goal is to promote the evidence-based communication of numbers in health. And I'll just start by saying that I think everybody listening here recognizes that numbers in health are ubiquitous and easier to obtain than ever before. So patients have access to their medical records. People in the public are buying apps, and things like COVID data are now publicly available in ways that they really never were. Unfortunately, again, I think this audience knows that we have a lot of people who have a lot of challenges being able to use this data, either because of low literacy or low health literacy. And I'll just mention that as far as we can tell, low numeracy is actually more prevalent than low literacy. So this is the ability to access, understand, and apply numbers to personal decisions, particularly in this case in health. So we have this sort of fire hose of data and numbers available to members of the public in this country, and yet we also have this problem where people may not really be able to make sense of them and apply them to their own decisions. This is terrible news. We have a lot of people who have inadequate skills. This makes it unlikely that they'll fail to understand critical information, and we can't go back really and fix their education. So what do we do about this? I'll give a couple of clues that suggest that there is actually some good news. One of them is a really classic study published in 1999 in which women just waiting in a waiting room were given a pair of numbers. They were either given the pair on the left there, 1 in 384 versus 1 in 112, or they were given the pair on the right, 2.6 per thousand versus 8.9 per thousand. It might not be immediately obvious, but these are in fact mathematically equivalent. If you do the math, 2.6 per thousand does in fact turn into 1 in 384, and 8.9 per thousand turns into 112. So the women were given these pairs of numbers and were asked a very simple comprehension question, which is, which of these risks is bigger? And it made a huge difference what the format of the number was. So the 1 in X format is the one on the left, and only about half of the women in the waiting room could successfully identify that 1 in 112 was actually bigger than 1 in 384. And when we reformulated this as 2.6 versus 8.9 per thousand, 3/4 of women chose the correct answer. So we can see that the format of the number makes a huge cognitive difference in how easy it is to process the information. And the difference was even more stark for women with lower levels of education. I will fast forward to another more recent clue, which is one of Brian's studies. If you've logged into your patient portal account recently, you might have seen something that looks like this, where you have a blood test result. It gives you a number. It might give you a standard range in units. It might give a little H or L to give you some indication of what that number means. And Brian's team did an experiment in which they contrasted this standard format in your patient portal with a number line with labeled ranges. And we're able to demonstrate, again, these are two mathematically equivalent ways of showing the numbers, but the graphical format in this case drastically improved people's ability to make sense of this number and to place it into context and understand whether their result was high or low, whether it was extremely high or extremely low, or whether it was borderline. So they had a much more nuanced understanding of what that number meant. So I'm going to use these two little clues to say what this means is that when we try to define health literacy or health numeracy and say it's solely a property of the patient, that it's solely a set of skills that the patient has in their head, this doesn't actually really explain what we're finding in the research evidence. Instead, it would be much more accurate to describe this as a sort of a three-way interaction between a patient who brings skills and knowledge to the table, the person providing the information who brings communication skills to the table, and then any documents or artifacts or technologies that are also being used as part of that communication process, whether it's a patient education leaflet or an app or some sort of medical device that the patient's using. All of these can be designed in ways that support communication or hamper it. And what we see is that effective communication happens when these three elements are aligned, so that the patients can actually access the information they need and make sense of it. So that starts to bring us to I'll go back here for a second and say, how do we train information providers to communicate better? And how do we design documents and technologies that rely on best evidence to support that communication process? If we are just looking at words, there's actually a lot of resources out there. If you are interested in understanding how to write plainly for the public, particularly around health and medicine, AHRQ has guidance, CDC has guidance, plainlanguage.gov has guidance, and there's a tremendous amount of resources and self-education that you can do to communicate in a more effective fashion. But almost none of it really addresses numbers in health. The types of numbers, the types of pieces of evidence that we could provide are things like, did you know that if I tell you that the side effect is rare, that will tend to make you more worried than if I told you it happens in 1% of cases? In fact, we recently did a meta-analysis and we found that when we tell members of the public that an event is rare, on average, they think that means about 9% of the time, which is actually quite common, I think. In other words, by using that term rare, we're really miscommunicating what we're trying to communicate here. Did you know that if you say there's a 1 in 100 chance, most people perceive this as bigger than a 1% chance? Mathematically, of course, we know that's equivalent. But in experiment after experiment, people express more concern when it's expressed as 1 in 100 rather than 1%. And then finally, here's another example of graphic evidence. Risks and probabilities are more memorable when we present them as a field of little human stick figures rather than just as a human block, a set of blocks. Again, this is relatively well supported by the evidence, but I don't think that most communicators know this. So this is the motivation for the Making Numbers Meaningful project. We are funded by the National Library of Medicine to try to collate and disseminate this evidence about how to communicate numbers. AIM 1 has been a very large systematic review about how data presentation formats affect comprehension, decisions, behavior. AIM 2 has been to not only publish the evidence, but also to build an interactive guidance system that would be available for communicators who want to know how best to communicate this information. And then to assess the effect of the system on professionals who are making decisions. This has been a major team effort, and I'll just give a quick shout out to the team. Brian and I have been working with colleagues at Cornell, NYU, and then an expert panel of people whose opinions we really respect in risk communication and health literacy from around the country. Here's the scope of the systematic review. It's been very large, and the reason is that our inclusion criteria have been pretty broad. We are interested in experiments and quasi-experiments that directly compare two or more formats for presenting health-related numbers. We are limiting it to studies that measure quantitative outcomes, having something to do with behavior, comprehension, perception, or attitude. We're limiting it to adult participants without training in health or medicine. There's no date limit, and we have included a number of articles in other languages, which we've had professionally translated. This has led to, after a number of screening steps, we've whittled this down to 405 articles, which is still quite a very large systematic review on risks and probabilities, laboratory results, patient-reported outcomes, environmental data, all sorts of other sorts of health and medical-related numbers. Our team has developed a risk of bias evaluation and conducted pairwise evaluation in each one of those studies, and a standardized data extraction and summarization process. So Brian will then talk a little bit about the structure of the types of papers that we've included.
So as Jessica alluded to, the challenge here is that the studies can be covering many different types of things. So I'm going to start by walking us through the terminology that we've been using consistently in this study to help you orient to all the different ways in which we're trying to slice and dice the set of papers that we've identified. So first, most of the studies in this review follow the structure you see here. So there's some kind of stimulus, which includes what we want to think of as separately the data, and then the data presentation format, the way in which that data was presented. That then allows a participant, a recipient of that communication, to do a task and results in a particular outcome. And I'm going to walk through each of these pieces in turn so that you get a sense of this structure. So the start here is the stimulus contains some data. So if we're talking about some data in a graphical format, this is a risk, a probability. That's the type of data. It's a 31% represented in this case in an icon array graphic structure. And we could represent it in percentages. We could represent it in a bar chart. Those are different presentation formats. So next, but let's think about all the different data structures that are possible here. So we recently published a paper that is online available now. It's not yet into an issue in risk analysis. That is a set of taxonomies that we've developed as part of this project. And the first taxonomy I want to talk about is the data structure taxonomy, in which on the vertical column, we're separated the distinction between what we might call single data pieces. So one probability or one measurement from a lab value versus an effect, which is a comparison between a pair of observations. So reducing a risk from 7 to 3%, having a hemoglobin A1C level going down from 8% to 5%, et cetera. But then there's also this horizontal level where it represents increasing sort of layers of complexity of data. So the top row is the basic level, where we're just talking about sort of either a single variable Could be a good variable, could be a bad variable. But then we've also separated trade-off situations. These are situations in which there are two or more trade-off variables, some positive, some negative, that are being tried to compared within that context, decision context or communication context, as well as, of course, time trends, where you may have one or more variable, but it's being observed many points in time over, at different points in time. And so you have trends, you have shapes of those curves, et cetera. And this is factorial, right? You can have single time trends, you can have effect time trends, et cetera. So all of these different combinations may exist within the data sets that we have. So moving on, each of these types of data, of course, can be presented in many different formats. And so we're not going to have an exhaustive list here, but broadly, we have number type of formats, 1 in X, percentages, but also things like heart age. We have verbal probabilities, so verbal terms that are representing the likelihood, like rare or common. And of course, we have innumerable different types of graphics, bar charts, icon arrays, number lines, et cetera. And you see examples of these here. Okay, so now that we've established the data formats, it's also worth acknowledging what we've learned trying to just build a taxonomy of all these different things. One of them is this. If you look at this graphic, what is this called? Now, I have already referred to it as an icon array, but in our literature reviews thus far, I believe we have found 22 distinct terms that were used to represent graphics like this. That obviously is a nightmare, both from a review standpoint, but also from a communication design standpoint. If you don't recognize that you're talking about the same thing, we're not actually able to communicate effectively from one communicator to another. So that's one thing that's come out of this. But let's just not even go further there, because there's all other kinds of graphics that pop up as well. Now, once we get into this, we've got the data, we've got the graphical format. So then now let's talk about outcomes. So the researcher is going to present certain types of questions to the participant. How common is this side effect? How worried are you, et cetera? Those questions are different types. Well, we tried to build a taxonomy of the different types of outcomes. So on the next slide, here is the 10, well, it's actually 12 different categories here, and I'll talk about why I said 10 first in a second. Each of these represents a different type of outcome. So we might have identify, so look up in the data stimulus, find a particular number. Now, if that's available to you, it's what we'd call that an identify task. But if it's been removed from you and now you have to rely upon your memory, that's a recall task. We also have things like what we call dominant tasks. So being able to look at a set of numbers and identify the highest one or the lowest one. Then sort of in the middle there, you've got things like what we would call perceived or subjective probability. So this is your estimation of the likelihood of that event or your affective response. So this would be like, how worried are you type response. Notice right next to it, we also have perception of difference. And that's an important distinction. Like you could have a perception of an individual piece, or you could be comparing multiple data points and having a perception of the largeness or smallness, the worrisomeness, et cetera, of that difference. And then down towards the bottom, we have things like behavioral intention, actual observed behavior, as well as your preference for the way in which the information is presented or your trust in that information. Each of those represents a different outcome that can be measured and appears within the literature. Okay, so next slide. So we've got data and format, and then we've got outcomes. And then when we try and put these things together, we have to recognize that requires, the combination of those things require the participant to exert a particular kind of cognitive task, to examine the stimulus in a particular way in order to answer the question that has been posed. And so that then leads, yeah, go ahead.
I was going to say, and I'll take over at that moment for the next few slides. It's worth noting that in these experimental studies, this cognitive task is sort of prompted by the experimenter saying, how common is this side effect? And then the participant in the study then performs the cognitive task to answer the question. But out in the field where, real people are working on their real problems, presumably these cognitive tasks are things that people perform on the data, on the information in order to pursue their own goals. So these cognitive tasks themselves also fall into different categories. So this particular type of a question, if we asked you how common is the side effect, that would be what we call a point level task, because we're asking you about a particular one piece of information. We also have something that we would call a difference level task, which is a comparison here between two pieces of information. So for example, if I asked you here, I gave you two icon arrays, I asked you, this is your risk without the vaccine, and the one on the right is your risk with the vaccine. How effective is the vaccine? That requires this cognitive task of a comparison and in fact, kind of a subtraction of what the two risks are. So we call that a difference level cognitive task. When we went through the literature, we identified 4 groups of these cognitive tasks. The point level would be identifying a single point. Difference level would be assessing the difference between two different points. We also identified this trade-off level task, which is a sort of a more holistic cognitive task of choosing, for example, option A versus option B on the basis of both the information about both benefits and harms. And then a time trend level task, which is again, a holistic examination of the entire trend. So for example, I might show you line graphs versus bar charts for showing some survival probability over time. And I might ask you, which one do you prefer? And that would be a time trend level cognitive task. So as we have been grouping the literature to make sure that, whoops, okay. These studies, in fact, are all comparing are performing the same task on 2 different stimuli. And the question is, do we get different outcome when we show these different stimuli? The tasks, the outcomes then dictate the types of tasks that we are inferring that patients are doing on this information. Perceived probability, again, as I mentioned before, is a point level task. Perceived difference is a difference level task. And I've provided examples here of those trade-off and trend level types of tasks. I think an important insight here is that a single stimulus can support multiple different types of tasks depending on what the respondent is trying to get out of that piece of information. So they may be looking at just a single portion of that in order to identify a particular, say, risk, or they may be looking at multiple portions of the stimulus to compare them, or they may be looking holistically at the entire stimulus. What we then, oh, this is actually back to you, Brian.
Yes. So the challenge here, of course, is that having gone through all of these tasks, now the question is, so what are the relevant comparisons that we can start to examine from the standpoint of, how was stimulus A different from stimulus B? So what are the comparisons that exist within the literature? And you can slice this multiple different ways. We've chosen to organize this around the 10 comparisons that you see here, including number versus number format comparisons, numbers versus verbal comparisons. So is it better to use a number or is it better to call a risk rare? Numbers versus graphics comparisons. And again, that unpacks into numbers versus different types of numbers into different types of graphical formats. So there's a multiplicity even within that type of comparison, as well as graphic versus graphic comparisons. But I also want to mention things like often there are variations in what kinds of denominators are used to present probabilities. So out of 100, out of 1,000, out of 1,000,000, et cetera. We've looked at that format comparison. We've looked at whether animations or interactivity incorporated into graphics makes a difference. A key thing has been context, so provision or lack thereof of different types of contextual information, comparison reference points, things like that, as well as how to uncertainty is relevant, how it's represented, does it matter, framing things as gain versus loss, as well as the time periods that are presented. And each of these has its own evidence base. So next slide. The end result is an enormous, conceptually at least, multifactorial structure of evidence. So you have all these different outcomes, and I'm not even showing you all of these in the horizontal dimension. You have all of these different kinds of cognitive tasks, and within each square of that is evidence for each of the comparisons I've just talked about, some of which then unpack further into the different types of graphics or the different types of numbers, et cetera, each of which represents a set of evidence body that could be looked at as having conclusions or not based upon the available research. So on the next slide, the end result here is just a scope that I think we have been astounded by. I mean, if you really think about this, we need to think about summarizing the evidence in a structure that includes hundreds of different analytical groupings, because this is entirely factorial. Like, probabilities are not the same thing as quantity data. Each of these task groupings is fundamentally different. Each of these format group comparisons is fundamentally different. Each of these outcomes is different, and all combinations are potentially possible.
And really what this means is that we cannot then have some sort of blanket conclusion that says, for example, icon arrays are better than bar charts. We have to look more granularly and say, icon arrays are better for this, but bar charts may be better for that. Icons arrays may be better for illustrating a particular type of data, and they may be better for inducing some particular outcome that we're interested in, but they may be worse for other outcomes that we're interested in. So that's where the complexity comes in this literature review. And I'll give you a particular example of one hypothetical research study. So let's imagine a research study that showed icon arrays, bar charts, and 1 in X numbers, like 1 in 10 or 1 in 20, to illustrate the chances of colon cancer with and without regular screening. So I can tell you right now, we've got a number of studies that sort of follow that format. In this study, let us imagine that the research measured the effect of these three different formats on the perceived risk of colorectal cancer, but also on the perceived effectiveness of the screening itself. In this hypothetical case, that single study would produce 4 records in our database of evidence, contributing evidence, I guess I'd say. The first one here is a point level task. I mentioned here that one of the measurements was on the perceived risk of colorectal cancer. Okay, so that's a point level task. How do you feel about the risk of colorectal cancer? The outcome being measured is perceived probability. The stimulus is, we've got this effect data presented as either icon array versus bar chart for a graphics versus graphics comparison. But we also have a numbers versus graphics comparison, possible for the same outcome here. The perceived probability, we could also look at the icon array and bar chart versus the 1 in X number. So right there, we've got 2 potential records in our database, one for graphics versus graphics and one for numbers versus numbers. And that's just for the perceived risk of colorectal cancer. But notice here that the researchers also asked about perceived effectiveness of screening. So now we have 2 additional records here, one graphics versus graphics, one numbers versus graphics for people's perception of the effectiveness of screening. This is a difference level task. We're asking them what's the difference between your risk with and without screening. So we would end up with 2 records at that level as well. So this gives you a little bit of a sense of how, even though we have 400 studies, we have several more hundred study records, or what we're calling TOSC records, in our database. And that ends up being our unit of analysis, this task outcome stimulus comparison, or TOSC record. Each single study that asked participants to look at a particular stimulus or a pair of stimuli and measured a particular outcome requiring particular cognitive tasks, and which was designed to experimentally test particular comparisons, such as graphic versus graphic, or numbers versus numbers, or graphics versus numbers. As we created these TOSC records, we had different members of our team review them. And this was primarily myself and Brian with our co-investigator, Natalie Benda, as a third reviewer in cases when there was conflict of interest, because one of us had actually co-authored one of the studies. We ended up creating 1-sentence takeaways for each one of these. But I think more importantly here, we assigned each one a credibility rating. And this was a combination of the risk of bias, the standardized risk of bias for that study, as well as a credibility score about the study design for that particular outcome. I will say, for example, in this situation, we can imagine a study where the primary outcome was, let's say, perceived risk. And that's what the study was designed to assess. That's what the power calculation was calculated on. And there was a large sample size for that one. That might end up with a high credibility rating. But that same study could have had a secondary outcome, let's say, of long-term behavioral follow-up. We could then follow these patients over a year and see if they actually got their colorectal cancer screening. That might be a secondary outcome. Maybe there was high loss to follow-up, and we don't have as many patients at that point for the behavioral outcome. So even though the study was well designed and was something that we would generally have a high opinion of, this particular outcome, we might give it a lower credibility score because of that loss to follow-up. So that's an example of the type of reasoning that goes into these credibility scores. We then grouped these and assessed the consistency within each group of evidence. We created synthesis statements summarizing all of the evidence within each one of these groupings, and a series of evidence statements summarizing the strength of evidence for certain conclusions on the basis of that evidence, and classified those with strong, moderate, weak, or insufficient levels of evidence. And I'll have Brian give some examples here of the types of evidence that we've generated out of these.
So this is one table from one TOSC set of stuff. So we've got, this is the numbers versus numbers guidance for point level tasks in which the outcome that was assessed was perceived probability. And even within this, there's a set of specific guidance statements which vary on their degree of evidence. So at the top here, going back to the beginning of the talk, so 1 in X number formats as compared to X in N or percentages tend to increase perceived risk as measured by perceived probability, as also we have separately looked at as measured by risk feelings or subjective perceptions of probability. And so you see an example represented there. Now, if we go down a couple rows, we might see, for example, emotional concern about side effect risks may be higher when benefits are presented before risks versus in the reverse order. So this is a finding that does exist in at least some studies, but not strong enough that we would give it a strong evidence-based recommendation, just simply stating that there is some evidence that goes in that direction. And then down at the bottom,
Brian,
yeah.
I was going to jump in because there was one question that I wanted to address here, which is that we've given this example of 12% less than sign 1 in 8. This is not us giving a blanket recommendation that 12% is worse somehow than 1 in 8. What we're saying is that for this particular issue of perceived risk, people's perception of risk will tend to be smaller with 12% than it will be with 1 in 8. Now, whether you think this is a good thing or not depends upon your communication goal. If you are concerned about inflating people's sense of risk, and I think we can all in public health think of a lot of examples where we really do not want to inflate people's sense of risk, then we might interpret that to say, oh boy, we really better avoid that 1 in 8 type of formulation. We certainly have other situations where there may be a concern that people do not have a sufficient degree of perception of risk, in which case you might choose to apply that particular guidance in a different way. And this is just for perception of risk. So this is not for any of the other outcomes. So anyway, sorry.
And that's related to the point where I'm going to. So this is focusing specifically on the perceived probability. If you have an underlying, for example, behavioral intention motivation, we have a separate data set of evidence-based guidance representing whether or not there is evidence that using these formats would increase or decrease behavioral intention. Now, conceptually, you might think that perceived probability would naturally flow into behavioral intention, but we've looked at this separately because it's not automatic. And so that's part of the point of having people think through, what is it that you're trying to accomplish? What is the outcome that you're focusing on? And for this evidence base, it's on perceived probability. Now, just to show you some more examples from this on the next slide, the first page was on numbers versus numbers comparisons. This next slide is on numbers versus graphics comparisons. So if we look at the top one here, part to whole icon arrays are associated with lower perceived probability as compared to X in N or percentage number formats. That's the evidence statement, and there's strong evidence available in our data to support that. But notice even there, we have some questions about, there's insufficient evidence to determine whether this effect holds true for emotional reactions. So we have evidence on cognitive perceptions of probability, but there is not sufficient evidence to have the same statement have as strong a recommendation in the context of emotional perceptions. And you can see a variety of other statements here that at least some papers have tried to compare directly. Like, we're only listing here things for which a paper did do a direct comparison and rating then based upon our credibility judgments and the quality of the studies to what degree the evidence supports a conclusion on that comparison. And just to keep going to show all the examples on the next page, we've got a little bit more additional information related to comparisons of numbers versus verbal probability or graphics versus graphics comparisons. And so, oops, actually, we didn't copy the table right there, but but you can get a sense of the types of each one of these tables represents one of these sets of comparisons that we're representing all that could be learned from the set of papers that we've been exploring.
So I think that probably everybody here would agree that what we're ending up with is a pretty unwieldy list of evidence. What we've done our best to parse out the different types of research that has been done and make sure that we're comparing apples to apples and providing evidence that actually is always apples to apples and never apples to oranges. The problem is then there's all of this evidence and it's divided up in all sorts of different ways. So we are in the process of now writing up a bunch of papers, but one of the, I think, most exciting products of this research project is not the papers, but an interactive website where we hope that people like you might be able to come answer some questions about what you're trying to do, and then we would be able to direct you to a smaller set of evidence that's actually relevant to your professional goals. So here's the development version of our website. There's some caveats here, but what we're trying to accomplish. When you begin, we ask you first, what is the response that you're hoping to provoke in the readers of your material? Do you want them to feel more concerned about something? Do you want them to feel less concerned about something? Do you want them to remember something? Do you want to provoke some certain behaviors? So we're asking you a little bit about what your top priority is. After you've answered that question, we then ask you a series of 4 questions about the data itself, about what you're trying to show. Is it a probability or is it a quantity? Is it a single number or is it differences between numbers? Is it at one time point or multiple time points? And is it a trade-off? After you've answered those questions, we then give you a results page, which we're currently tweaking, I would say, that would allow you to see, here's your numbers evidence, and then there's some interactive buttons here that would allow you to explore some of the other strong evidence and would allow you to also see the weak and insufficient evidence. Probably the strong evidence is most helpful for people who are actually trying to design communications, but the weak and the insufficient evidence, I think, is also pretty interesting because, for example, it tells you areas where we can't tell you what the right answer is, and so therefore your judgment is the best guidance. It also suggests, here's some areas for future research. We don't actually know whether A is better than B, and we're stating that here on the website so that perhaps we can stimulate future research in this area.
I just jump in one thing here. One of the things that we had to really wrestle with is how much weight to place on a given study. So there's a number of places within the evidence where there may only have been 1 or 2 studies that really specifically assessed one particular type of comparison about a particular outcome. And when that study is done well, one of the challenges, like how much should we trust? I mean, it's only one study, but it was a well-done study. One of the rules of thumb that we built into our evidence review was that no matter how high of a credibility we rating, if it was only one study, that was just going to be weak evidence. So some of the weak evidence statements are things that come from single studies that were well designed, but with only one study, we're not going to be willing to put any stronger support for that statement than just a weak level.
Great, and we are trying to reveal that we made a distinction between weak and insufficient, and we also made a distinction between insufficient because there were no studies, or the only studies available were very poor quality, but also we had a class which was insufficient because of conflicting evidence. And those are some areas where there are studies and they came up with different answers, and therefore we really don't know what the right answer is. And I'll just, in brief, one of the areas where we had a lot of conflicting evidence was about reader preferences. Do people like bar charts more than they like icon arrays? Do they like numbers more than they like percentages, or vice versa? A fair number of studies have assessed this, and they've all come up with different answers. So as far as we can tell, probably people's preferences are probably influenced by what's familiar to them. They may be influenced by what they're trying to accomplish with the data. That makes it very hard to draw any general guidelines about people in general prefer A versus B. So once you get to the preference section of our website, you'll see a lot of insufficient evidence due to conflicting evidence. And that I think is worth disseminating. As we're building this, we are right now in the process of user testing and user needs analysis. So we are interviewing people who are professional communicators or developers, people who are in the business of trying to present health information and specifically health numbers to the public or to patients, and assessing things like how do they tend to do these tasks on their own, and how do their judgments change if we show them the evidence, if we show them the guidance. Do they find our guidance easy to understand or hard to understand? Do they find our guidance credible, and does it actually help them to make evidence-based judgments? And if not, what can we learn from this to help people use this information better? We are in the middle of writing up a bunch of publications and from the basis of the systematic review, and we hope to publish the website and make that freely available later this year. So I will say, in summary, I think the take-home point here is that since we cast a wide net, we are really trying to be able to provide guidance about how to present numbers to the public. And that in itself is a very large and challenging task. In order to be able to synthesize the evidence, find the evidence, synthesize it, and present it to potential communicators and users, we needed to come up with a classification system that would allow us to come up with a standardized vocabulary and conceptual structure for what was the stimulus. And the stimulus contains data that's presented in some sort of data presentation format. And we ended up having to come up with lists of types of data and lists of data presentation formats in order to standardize that. We also need to take a look at the outcome that was assessed, or the response that was provoked by this piece of patient education material, or the stimulus. And as we looked at it, it was very clear that the same stimulus could be good for one outcome and bad for another outcome. And only by breaking it out by outcome could we really elucidate those differences. It was also, we also had to collapse a lot of the evidence according to the cognitive task that was conducted. In other words, was this a relatively simple cognitive task of looking at one little piece of information within the stimulus, or was it a much more complex task of making, for example, a risk-benefit judgment trade-off? And then within the study design, what were the types of stimuli that were compared? Were these different types of graphics? Were they numbers versus graphics? Were they numbers versus words? And only by classifying the literature by stimulus, outcome, task, and comparison, can we be confident that we are comparing to apples in the literature and synthesizing evidence-based recommendations that really are on the basis of a homogeneous group of evidence that allows us to make strong conclusions. So with that, we'd be happy to circulate this and also some of the publications that have come out of this project to date. We're hoping for a number of more publications in a short period of time. And with that, let me open this up to questions. I see some questions in the Q&A, and I think chat. No, just Q&A.
Hi, well, thank you guys so much. I'm happy to have you guys answer the questions directly in the chat or read it. What makes is either.
Well, why don't I start by just leaping into one of the questions that's there. So Rob Ham, hi Rob.
Hi Rob.
The question here is, should informing people this display will make people more concerned be simply stated? It seems to offer people who want to sell something a manual. How do we advise against such self-serving behavior, or is that beyond the scope of the aid? This is a question that we wrestled with. As we start to break apart the outcomes and we look at the questions of, what is it that the communicator is trying to achieve? As Jessica has alluded to, like some of these techniques can be used for self-serving purposes, to make people afraid of things, to steer people, to make people more motivated to engage in a behavior. Now, whether you want them to engage in that behavior or you don't want them to engage in that behavior, it's persuasive. And we are documenting what evidence exists that has that effect. I mean, I think the truth of the matter is, as we unpack the effects of numerical communication, we are both creating a manual for persuasion and a manual for debiasing. These techniques can be used for different purposes, and it's only by awareness of what is it, the implications of using this format versus that format, that we can then hopefully, at a minimum, ensure that communicators know what it is that they're going to achieve when they choose a particular approach to communicating their number, and to potentially steer people towards more evidence-based recommendations that will align with their goals and potentially increase essentially the communication literacy of the communicators to help them be better at their task.
Yeah, but I would say, Rob, we've definitely wrestled with this, and I think any communication guidance can be misused in the wrong hands. Even the plain language guidance can be turned on its head so that certain information is actually deliberately made more complex so that readers don't have access to it. I think we share your concerns, but I think it's being transparent about what the evidence shows is the direction that we've chosen to go. I can take the next one about statistical significance.
Sure, go ahead.
Which, that's a great question. The question is there evidence about how to show statistical significance in graphics, but I would say even in other forms. And we ended up not focusing on that, I would say, because we ended up deciding to limit this to lay audiences. So we excluded studies that were studies of physicians, studies of scientists, even studies of medical students. That then ended up focusing much more on sort of more general concepts rather than statistical significance. I myself am very interested in this, and I think that it's been used and misused and definitely used to bias as well, but I can't say we can answer that with this particular evidence review.
I will say some of the principles that we came up with in crafting this review could be used to good effect in studying different methods of communicating statistical significance. I'm thinking now about, the evidence related to provision of contextual information. So how does providing additional information help people to calibrate whether something is large or small in a particular category or not, et cetera? That work has been done less in probability space, more in quantity space, but it has similar implications for thinking about how do we want to communicate the implications of a certain degree of statistical significance. Whether you're talking about an odds ratio or you're talking about a p-value, there's some common threads to those kinds of issues. I was just going to go back to the original question here. So someone posted about a slide we included fairly early on in the presentation that compared 1% versus 1 in 100. Let me be clear about what we said. What we said on that slide was, if you say a 1 in 100 chance, most people perceive this to be a larger likelihood than a 1% chance. That is not saying that they necessarily are more worried about it. That's a different outcome. That's a perception of an emotional, subjective response as opposed to a cognitive perception of what is the magnitude of that risk. And I also want to be clear that that doesn't necessarily mean that they understood it better. Like, it's a separate question to ask whether or not they could remember that weather or be able to pick it out of a table easier. Those are, or if there was a set of numbers all in percentages or all in out of 100, whether they would have an easier or harder time finding the largest number. Those are each different outcomes, and the evidence base is not necessarily consistent from one to the other in terms of whether or not the format's going to make a difference or not. So that's what we're trying to drive at here. So what does that mean for, the follow-up question here was, what does that mean for pictographs or icon arrays that also help people understand GIST information? I'm just repeating the question here. By using a frequency framework, often using the presentation of X patients out of 100. So there is an important question of numerical representations of X out of 100 versus graphical representations like icon arrays, which visually show that. That's part of why we have the graphics versus numbers comparisons in our review. I also wanted to comment that we've intentionally avoided using the language of GIST, in part because GIST often means different things. Sometimes it means comparison. Sometimes it means being able to categorize something. And we've tried to get a little bit deeper so that it's very clear what the specific cognitive task was. And I think that the main point here is that we can't necessarily automatically generalize from one piece of evidence to a different piece of evidence. The evidence base from comparing numerical representations in frequency format does not necessarily always carry forward to graphical representations that emphasize individual frequencies, like icon arrays, versus those that don't, say a bar chart or a pie chart. And that's why we're doing this so on such a granular level.
So let me give one additional example of exactly what you're talking about here, Brian, which is, okay, so here's a situation where this one on the left, the 1 in 384 versus 1 in 112, that's what we call 1 in X format. This evidence, this experiment, and actually a very large body of evidence clearly demonstrates that this 1 in X format is worse if you want people to be able to compare numbers. So that's often considered part of GIST comprehension. Which number is bigger? Is this number larger than that number? This 1 in X format is definitely terrible for that. So we can very strongly say, avoid that if you want that kind of basic level of comprehension of saying, be able to rank these numbers in order of their magnitude. However, an equally strong body of evidence does suggest that 1 in X format makes people more, it makes people think that risk is larger. I tend to agree with Rob here that I'm not crazy about inflating people's sense of risk, but we certainly have worked with medical professionals who are concerned that patients don't have an adequate understanding of some, relatively smaller risk events, and they actually want to draw attention to those smaller risk events. So that could be an example where this 1 in X format is good for that purpose, but bad for this other comprehension purpose. So I think that sort of explains what we're seeing in the evidence, which is that the same format, the same graph could be better for certain purposes and worse for other purposes.
Well, and coming from the public health school as I am, many of my colleagues are primarily interested in communications in the context of very persuasive health messaging, getting you to quit smoking, getting you to exercise more, et cetera, situations in which there's no ambiguity. We are trying to be persuasive. And in that context, using a 1 in X format may align with the communicator's goal. Now, we have to talk about the ethics of that. But if you're talking about motivating people to get COVID-19 vaccinations, I might be comfortable using this tool to accomplish that goal.
Let me jump to Catherine's question here in the Q&A, which is, if the goal is to provide balanced information, communicators could use 2 methods of showing the data that tend to bias in opposite directions. And I think that that's a great point here. And in fact, believe it or not, there actually is some evidence about that, particularly in the realm of framing. So gain framing versus loss framing. There is some evidence about how combining different framing formats can help reduce bias. Another one is adding icon arrays. It can reduce some of the biases that come from numbers. Another piece of evidence is that adding personal anecdotes about some friend of yours who got a disease inflates the bias. So we actually do have evidence about that. And I think, Catherine, your point there that the question about combining these things to cancel out bias, I think, is a very good one, and potentially would be supported by a lot of the evidence that we've got here.
Potentially, but I will chime in with a counterexample. So there is the work on what was often referred to as the drug facts box format for presenting multiple side effect risks from a particular intervention. So I'm thinking of a paper that we reviewed as part with Woloshin and Schwartz as lead authors on, where they did a direct comparison of a tabular format that only had percentages versus a tabular format that only had X out of 100 versus a tabular format that had both. And the one that had both did not perform better on certain outcome measures, in part perhaps because of the complexity. You're having a redundant presentation of the information, and for highly numerate people that may be okay, but for less numerate people that's just more numbers they have to process. So again, diving really deep into this helps us to unpack when is that going to be a positive thing and when might it be a negative thing.
That's a great point. And I think the second part of your question was, could this be used as like an educational tool to try to train people to question the numbers that they are receiving? And I think that's a great point. I actually do, sort of separate from this, but somewhat informed by this, I do regular workshops with journalists about interpreting numbers in science and conveying numbers in science, and particularly health and medical reporting. And one of the main points is to try to get them to understand how their own perceptions are potentially being manipulated by either advertising or, to be fair, even scientists who are trying to make their results look cooler. And try to get the journalists to be comfortable with potentially reformatting these numbers, or at least questioning why they're getting the number in that format.
We're running out of time, but I do want to just mention as a last point related to that, that's a really critical piece if we've been thinking about all the data that has been flooding us related to COVID-19 and case counts and things like that. Like, the data is appearing in lots of different formats that may be the way in which it was originally collected. Is that necessarily the format that's most useful for accomplishing our communications goals to the public? Often not. And so part of our larger goal here is to help people realize that being aware of what you're trying to accomplish and then being open to the idea of transforming information into different formats to accomplish those goals may be a key thing to clear communication.
Great.
So I think we are at 3 o'clock.
We are 3 o'clock, yeah. But yes, I would recommend How to Lie with Statistics. Good book.
1954, I think it is. It's ancient, but still quite applicable.
Well, I'll just be the one to jump in and thank you both for a really interesting conversation. And thank you so much with engaging with all those great questions. So thanks to our audience as well.
Thank you. And
thank you so much for having me.
Absolutely.
Bye, guys. Thank you.
Bye-bye.